Good morning, class. Today we're going to look at lesson number 17, on how CO2 is changing the climate. We could do like a whole course on how CO2 is changing the climate. It's a really big topic, and I'm going to try to cover it in one lesson, just so we can kind of get through this topic and on to water cycle, just so we can kind of even just cover it a little bit. So I'm going to go through this, and then I also have an extra link for you here that if you want to learn more about the carbon cycle, it's a really good resource. And then if you have any other questions, if you're curious and you want to know more, I can also find some other links for you and some other resources for you, or make some of my own if you want to learn more. I just don't want to give everybody too much work, so I'm going to keep it kind of more to the minimum. But if you want more, please reach out. So what is CO2 and where does it come from? So CO2 is carbon dioxide. So it is a carbon atom that has two oxygen atoms bonded to it. And it makes up a molecule that we call carbon dioxide. So at room temperature, CO2 is a gas that has no color. At low concentrations, CO2 doesn't really have a smell or a taste, but at higher concentrations, it can taste bitter and acidic. CO2 freezes at about negative 78.5 degrees Celsius, and we commonly call frozen CO2 dry ice. So if you ever work with dry ice, that is just CO2 that has been cooled down and frozen. There is a liquid stage in there, but commonly we only see CO2 as ice and a gas. So CO2 is produced many different ways. So a couple of ways are from breathing. So any animal that uses respiratory or cellular respiration to live, breathing, is going to breathe in oxygen and is going to breathe out CO2 or carbon dioxide. So whenever we are breathing, humans are actually putting more CO2 into the atmosphere, as well as livestock. Any animals that breathe also put CO2 in the atmosphere. Um, when organic matter decays, it releases a lot of CO2. Burning wood or fossil fuels also release a lot of CO2. And then breaking down in carbonate rocks. So when you break down carbonate rocks, that carbonate gets released as CO2, carbon dioxide. And this happens with weathering. It also happens in industrial processes like making cement. When you make cement, a lot of the time you take carbonate rocks and you bake them. When you bake them, you actually release a lot of that carbon dioxide into the atmosphere. So a large part of the CO2 that's released in the atmosphere is surprisingly due to cement. So many different ways again. I just went over a couple here, and we'll look into a couple ways in more detail when we look at what we can do to stop CO2 from being released into the atmosphere, or at least limit it. It's really impossible to stop because natural processes produce CO2 in the atmosphere, like breathing, or weather, or volcanoes. We talked a lot about volcanoes emitting CO2 in the atmosphere. They do that as well. So it's really trying to reduce the amount of unnatural CO2 we put in the atmosphere. So all the looking at every factor that puts CO2 in the atmosphere, and each year we put about 44 billion tons of carbon dioxide into the atmosphere. And that's a big number. It's hard to comprehend. So let's look at it, the percent of CO2 put in the atmosphere and how this affects the parts per million. So parts per million, again, if you have 1 part per million, for every million particles, or every million molecules in the atmosphere, one of them will be CO2. And right now we're about like 300 and something parts per million. And it may not seem like a lot, but it can have, even just increasing that a little, can have drastic effects. And we'll talk about those effects in a second here. So each year, we increase the parts per million by 2.3 parts per million. So after 10 years or after 100 years, we would have almost doubled the amount of CO2 in the atmosphere, which is crazy. So that is about 19 billion tons of CO2. So about, on average, about 10 billion tons of CO2 equals about 1 part per million in the atmosphere. It's a bit lower than that, but it's about 10 billion to 1 part per million. So you may notice this number is a lot smaller than the amount of carbon dioxide we're putting into the atmosphere. So this is how much ends up in the atmosphere after like one net year. So this means that Earth's oceans, forests, and other ecosystems are actually soaking up about 57% or 25 billion tons of carbon dioxide that we emit into the atmosphere each year. And this 57% is actually an interesting number. Based on data, I couldn't find clear graphs on this data, so I didn't include it. But data has shown that consistently, even though as the amount of CO2 we're emitting each year increases, the Earth is only able to absorb 57% of the CO2 that we put out. So the more CO2 we put out, the more Earth absorbs, but 43% is always left over. And this goes for majority of CO2 outputs. But if we go to the extreme, Earth can only actually absorb so much. So it's said or predictions based on simulations have shown that by 2010, or by, sorry, 2000, what is it, 21, 0? How do you say that? By the year 2100, there we go, Earth will actually be emitting, or we will actually be emitting so much CO2 that we reach the maximum that Earth can absorb. So the pattern breaks at the extreme limits. If we don't emit much at all, Earth will actually absorb more than we emit. So the CO2 levels can actually decrease, which is what we want. So we want to get to a point where we are only emitting what Earth can absorb. So Earth is absorbing 100% of the CO2 we're emitting, so the CO2 levels stay consistent. If it's over 100%, the CO2 levels are going to drop. So if Earth is absorbing more than we put in, so over 100%, the CO2 levels will drop. If it's under 100%, the CO2 levels will rise. So throughout Earth's history, we've shown that CO2 levels have increased and decreased, and they've gone through spikes. But what happens is, once the CO2 levels increase, they stop increasing. The process that emitted the CO2, like a big volcano or a meteor, stopped. So the CO2 levels were able to decrease. But when we emit CO2 in the atmosphere, we're not stopping. So there's no point in time where Earth can recover. And this got me thinking, well, right now, we are stopping emitting CO2. People are driving less, planes are flying less. Our carbon footprint is a lot smaller. So is Earth having a time to heal? Well, not really. We've only actually dropped our CO2 emissions this year by 5%. That's it, 5%. I thought it was going to be way more, only 5%. So we're still at 95% CO2 emissions. And for experts say, for us to actually reduce our CO2 levels, we need to drop our CO2 emissions by at least 50%. So we're 10 times smaller than what we need to be, even in this drastic, even in these drastic measures where people are staying at home, not able to drive or fly. Our CO2 levels still need to drop by 10 times what they have dropped in the last couple months. So it's crazy. So it's going to take more than fewer cars on the road and less coal being burned. So coal is much worse for emitting CO2 than oil. Now, oil is pretty bad, but coal is even worse. So it comes down to rethinking industry, rethinking how things are done so that we can really reduce our CO2 outputs drastically. And we'll talk about this next week because there's some really interesting things people are doing that's going to reduce the amount of CO2 in the atmosphere. So we are making steps. It's just these steps need to come quicker than they have been. So let's talk about how CO2 is affecting the climate. Now, I was pretty short on this one because essentially it's just one idea. So what happens is we've looked at Earth's atmosphere, and what it does is it absorbs a lot of infrared light or a lot of radiation from the sun, but it lets visual light in. So that visual light gets passed through the atmosphere, hits Earth's surface, and reflects off. So some of it's absorbed and some of it reflects. We talk about reflectivity. So the higher the reflectivity, the more that gets reflected, and the less it gets absorbed. When light is absorbed, Earth warms up. When it's reflected, it's good. So sometimes when this light gets reflected, it's going to lose energy. So instead of being visual light, it loses energy and becomes infrared light, which is essentially heat. So it bounces off Earth and it's going to leave as infrared light. And oxygen and nitrogen, majority of the chemical or the majority of the molecules and atoms in the atmosphere let this infrared light pass through. But it is the greenhouse gases, so CO2, water vapor, methane, majority. There's some other ones, but those are the main three that are actually going to absorb this infrared light. So the gas will absorb this light and it's going to warm up the atmosphere around it, and it's going to warm up so the atom gains energy, and then it's going to release that energy in a random direction, and that random direction can be towards Earth. It could be to space, but it could be towards Earth. So the more greenhouse gases or the more CO2 we have, the more of this infrared light is going to get absorbed, and the higher chance for this infrared light to be passed back towards Earth. So even if we reach, like we're absorbing all the infrared light, the more we have, the more of this infrared light, this heat that's going to get directed towards Earth, and the less is going to get directed into space. So I wanted to go a little sciencey here, and this is actually has to do with quantum mechanics, which I thought was kind of interesting if you talk about quantum mechanics in earth science class, very basically, of course. So CO2 has is a molecule that has atoms in it, or has electrons in it, and electrons are going to orbit the proton or the nucleus. So classically, we think of the nucleus and we think of electrons orbiting. So this would be like a helium atom, one proton, and you got your electron orbiting it. And electrons kind of take up some spaces, but they have what we call energy levels. So they have really precise energy levels. So if you get the right amount of energy, it can actually electrons can jump to the next energy level, and the atom will gain energy. So the CO2 molecule has atoms in a state where infrared light actually has the perfect amount of energy to bump the electron up one stage. So as that electron gets bumped up one stage, the the electron gains energy, so the atom gains energy. But it's unstable at this stage, so it's quickly going to drop back down to the lower stage. So it's about 0.020 is 1, so 10 to the negative 20 seconds. So like instantaneously, it drops back down, and it's going to re-emit that infrared light in a random direction. So that random direction could be up towards space, could be down towards the Earth. But the more atoms we have, the more CO2 atoms we have, the higher chance that infrared light is going to get directed towards Earth, and the longer the infrared light stays in the atmosphere, warming up the atmosphere. So hopefully that wasn't too confusing. I had a nice GIF of it here, but it doesn't seem to work on the PDF. I guess that makes sense. So I'll might just attach the GIF as well. So if you want to have a look at that, have a look at it. It just shows the light coming in, get absorbed, and being passed out in a different direction. Yeah, so that's the lesson today. If you have any questions, let me know. I'm going to have one bonus question on this site here. So this is talks about the carbon cycle, and just kind of how carbon get absorbed, how it gets passed out, how it gets filtered through, and it talks about natural processes. So there are definitely unnatural processes that are affecting the carbon cycle, and that are making it so there's more CO2 in the air and less carbon in the earth. So it does a good job talking about chemistry and talking about how the CO2 gets absorbed. Now, when it talks about examples of greenhouse effect, or examples of how Earth heats up and cools down itself, these examples talk mainly about when humans are not around. So we have disrupted the cycle, so Earth is warming up. These examples mainly talk about Earth cooling down, which happens, but with humans here, it's not happening. We are causing Earth to completely warm up. So just take that with a grain of salt. It's right, but we are affecting these processes and not allowing them to happen. Okay, so that's everything from me today. I hope you all have a great day, and I'll see you next time.